Good morning and welcome to Tech 240 for Wednesday, February 3rd. Let's take a look at the schedule before we get started on the material that we're going to talk about today. First of all, we see that we actually have two labs that are due today. This is the only day in the whole semester where there are two labs due on the same day. And the reason I did that, I think I've mentioned in the past, but the reason is because Lab 3 is, I know, a little bit more challenging, so I wanted to give you some more time to do Lab 3. So you actually had a little more than a week to do Lab 3, and unfortunately that kind of pushes it into the due date for Lab 4. The good news is that Lab 4 is pretty straightforward and not too challenging, so hopefully you shouldn't have too many issues with Lab 4. So Lab 3 and Lab 4 due at 11:55 p.m. tonight on ReggieNet. Lab 3 does not use Tinkercad. Lab 4, there is a piece that uses Tinkercad. All right, then moving down, we see that Lab 5 on LEDs is due by February 8th. And then looking at today, on February 3rd, on that row, we see that the material we talk about today is going to be relevant for Lab 6. And Lab 6 is going to be due on February 10th. And the last thing on the schedule I want to point out is we have Quiz 2 coming up. Quiz 2 is going to be due, as you can see, on February 7th. That's this Sunday. And Quiz 2 is going to include material up through and including the last class session on LEDs and diodes. So Quiz 2 does not include any material from the things that we're going to talk about today in this class. Today we're going to start talking about something that I would call kind of a separate mini topic within the first third of the semester. So far in the semester, mostly what we've been doing is what I would call circuit analysis, where I give you a circuit and you solve for all the unknown values in that circuit. You solve for the voltage drops across components and the current flow through the components and the resistance values sometimes, and basically just everything about the circuit that you could possibly want to know. In the last class session, we started talking about diodes and LEDs, and that's moving us toward the direction of what we're going to talk about today, because in the diodes and LEDs lab, you started designing your own circuits. You started putting the resistors together and calculating what the size of the resistor that you need is, and then putting it together in your own way. And no two circuits are going to look identical when you do that last lab, Lab 5. Today, we're going to start talking about something called control circuits. I didn't come up with that name, but it pretty aptly describes what we're going to talk about. It's something that's going to do something useful for us. So we're going to design circuits that do something useful for us. Like it might be turning on a light, as simple as that, or it might be to cause motion. Maybe it's to cause a cylinder to actuate and move position for a hydraulic cylinder. Or maybe it's to turn on a motor or to turn off a motor or something like that. But it's to control different apparatuses that we can control with electrical circuits. So that's what we're going to start talking about today. And we're going to get into that next time as well in a little bit more detail. So this is kind of two class sessions, today and the next class session, on control circuits. So what I'm going to do today, I'm going to make two videos. In this first video, I'm going to start by talking about switches, because that's one of the basic components that we need for control circuits. And then what we often use for control circuits are devices called relays. And relays, as you'll find out very soon here, relays are nothing more than the combination of some kind of switch and a solenoid. And we'll talk about what a solenoid is. But first, we'll talk about what switches are, and then we'll put together switches and solenoids to talk about relays. And then we'll talk about how relays can be useful for us and what we can do with relays. There are a lot of different advantages of using relays, and we'll talk about that. That'll be the first video today. In the second video today, I'll do a demonstration on Tinkercad, and I'll show how we can use relays in Tinkercad, and that's going to be a demonstration also that'll help you for Lab 6. All right, so that's the plan for today. We'll start talking about switches, then we'll build it up into relays, and then we'll apply that into Tinkercad in the second video. So to get started, I'm going to go ahead and share my screen. All right, the first section of this presentation focuses just on switches, and then we're going to put them together with what we call a solenoid, which we'll talk about. And that combination is going to form what we call a relay. All right, so here is our most basic switch. This might be what you're most familiar with when you walk into a room and you use your hand and you flick on the light switch. This is just about the most basic switch that you can possibly imagine. And here is a symbol for it. And we call this a single pole, single throw switch. So we're going to talk about some more complicated switches, but they're going to follow this nomenclature, which is to say how many poles do they have and how many throws do they have. So let's talk about what that means. A pole you can consider as an input. This is an input pin or an input terminal. This is where the current flows into the switch. All right. So this switch has only one input right here. Generally, we think about the current as flowing from left to right. All right. So the current is flowing along this way, and here is the input to our switch. So it has one input. So it has a single pole because the pole is the input. So a single pole switch has only one input. That's right here. And the throw, this one's a little bit more tricky. The throw is how many outputs does it have per input? Per input. All right, so this one has one input, so it's single pole, and only has one output connection per input. All right, so because of that, it's a single pole, single throw switch, which is the most common kind of switch, but it's not the most useful kind of switch. We'll talk about more useful kinds of switches in a minute. So here is a very basic circuit with a single pole, single throw switch and a light bulb. And when we close the switch, then no surprise, the current flows through the circuit and our light bulb lights up. By the way, we haven't shown this before, but this is the symbol for an AC voltage source. And we'll do a lot more with that in the last third of the semester. But little preview, that's the symbol for an AC voltage source. We won't deal much with that at all in this first third of the class. And when the switch opens back up again, then it prevents current from flowing, and so your light bulb turns off. All right, if I have two light bulbs, then what I can do is connect them in parallel like this. Why would I put them in parallel like this? Well, if I put them in parallel, then I know that they're both going to get the same voltage drop, right? So they'll have the same voltage applied across them. And if this light bulb is rated for whatever this voltage source is, 120 volts AC, then I want them to both have the same voltage drop, right? So I wouldn't want to put them in series. So I have put them in parallel, and they're both going to be controlled with this one single pole, single throw switch. When I close the switch, then they would both turn on simultaneously. They didn't, in the animation, they didn't turn on simultaneously, but they would turn on simultaneously in the real world. All right, or if I wanted to control the light bulbs independently, then I could move the switches, and I could use two switches. I could put one single pole, single throw switch on each branch of the circuit. Now I could control them independently. Close one, and that light bulb turns on. Close the other, and that light bulb turns on. All right, now the next kind of switch that we're going to talk about is just slightly more complicated. It's a single pole, double throw switch. All right, so the nomenclature is the same. We have a single pole, which means it has one input connection. So that's right here. Here's the input side. This is also called the common. This is the common connection for the switch, sometimes abbreviated COM. So for this happens to be a limit switch, but it's a switch for right now, all right? So the common, or the input, is right here. So you'd connect a wire to this screw terminal right here. That corresponds to this connection right here. So we have a single input, or single pole, and now we have a double throw. Remember, the number of throws is the number of outputs per input. And we have two output connections per input, because this is like a little, it's a switch that can move back and forth. It can pivot right here. That's how to imagine this, okay? It can pivot right on that input pin right there. So it can pivot, and it can either be connected from this connection to this connection, or it can be connected from this connection to this connection, all right? So it has a double throw because it has two possible outputs per input. All right, so we always draw the switch in the de-energized or normal condition, all right? Like you just pulled it off the shelf, all right? So you're not pressing on anything, you're not activating anything. That's important when we get to talking about relays, all right? We always show the switch or the relay in its de-energized normal condition, all right? So what we have between these two connections, we have a normally open and a normally closed connection. All right, so we always draw it, like I said, in the de-energized or deactivated state, like you just pulled it off of the shelf. So normally, this switch is going to have a connection between the input and this pin right here, this connection. So this connection represents our normally closed connection. It's normally closed, meaning there's a connection from this terminal or pin to the input. So this right here is represented by this screw terminal right here. So you can put a wire and connect it to this screw terminal right here. The other is the normally open connection. That's this one right here. So in its normal state, when you're not pressing on anything or activating or energizing anything, normally this connection right here is open. It's not connected to anything. All right, and that would correspond to this screw terminal right here. The way a limit switch works is that when something presses on it, like let's say a piston or something, when a piston is moving and it reaches the limit of its travel, then it presses on this little lever physically, it pushes on it, and that moves this switch right here. So that's the purpose of a limit switch. And those are the connections for a single pole double throw switch. All right, so this is what I just talked about. We have an input, which we call the common connection, and then we have a normally closed connection, and we have a normally open connection. And we can have normally closed or normally open switches just by using the normally closed or the normally open pin or terminal on those switches. So this is the symbol. By the way, you'll see all these symbols in the very back of your lab manual. I included those, all these switches and a bunch of other schematic symbols. All the symbols that you might need are in the very last page of your lab manual. So you'll see symbols for normally closed limit switches, which means that normally they conduct electricity through them unless you press on them. And when you press on them, then that moves this switch right here. And so when you press on them, then it opens the connection. So they no longer have a connection right here. So this is a limit switch, and this is a float switch. Think of like the level in a tank. As the level in the tank rises up, there's a float right here. And as the float lifts up, then it breaks this connection. It opens this connection right here. All right. Conversely, you can use a normally open connection, and you can have a normally open limit switch. So this does not have a connection here, no continuity through here for current to flow, until something presses on it or activates it and moves this switch right here. All right, so there's a normally open limit switch. Here's a normally open float switch. All right, here's another application. This is what kind of switch? Well, it has one input and it has two outputs per input. So it's a single pole, double throw switch. Okay, this is the symbol for a single pole, double throw switch. So sometimes you'll hear them referred to colloquially as a two-way switch. Sometimes you'll see that, but technically, it's a single pole double throw switch. So in an application like this, it could turn on one of the light bulbs, but not both at the same time. Okay. All right, but there's another application that I'm sure you've seen before, and I'm sure you've seen it before, maybe in a kitchen or a dining room or an entryway in your apartment or in your house. And the purpose of this arrangement right here with two single pole double throw switches is, if you think about it, you can turn on this light bulb by flipping either of these two switches. So, for example, in my house, I've got two entrances to the kitchen, kind of one on each side. And there's a light switch on each side, and I can flip either light switch and turn the lights on in the kitchen. And you've probably seen something like that. Some type of common area in your house or apartment might very well have an arrangement like this. All right. If you go to Menards, sometimes this is called a two-way switch. But if you look in a catalog and you're ordering one of these, I'll show you in a few minutes, they will be called a single pole double throw switch. So either one of these switches, if I change the position, then it's going to turn on the light bulb. So the left one, if I change its state, now I have continuity through this path. If I were to turn that one back off, then I break continuity. There's no way for current to flow through the light bulb. But now if I take the other switch, well, okay, I didn't show that, but you can imagine if I had taken the other switch and flipped it, then I would still have continuity to the light bulb. So either way, you will have continuity through it. The only way you wouldn't have continuity through it is if you changed both at the same time. Then you wouldn't have continuity and you couldn't have current flow to the light bulb. Oh, what happened here? Okay, did I go backwards accidentally? I may have. All right. Okay, moving on. The next one, this one in particular is not real common, but you will see it. This is a double pole single throw switch. Remember what these mean. The number of poles is the number of input connections. So here we have 2, 1, 2. And how many throws is how many outputs per input. So don't get confused here. There are 2 outputs, but there's only 1 output connection per input. So this input only has this output or nothing. And this output either has, it's either connected or it's not. So this has this input. So it's either connected to this or it's not. So there's only 1 screw terminal connection that's right here for each input. All right. So this one is not real common, but there are certain applications. This is one type of application. This is a motor over here, and it looks like it must be an AC motor that we'll talk about later on this semester in a month and a half, because it has an AC power source connected. And the switch that we're going to use in this case to connect or disconnect the motor is a double pole, because it has 2 inputs, single throw, because it has 1 output per input. So this is kind of a switch that offers a higher degree of safety or redundancy. I mean, this would work just fine with a single pole, single throw switch on one of these wires, either this one or this one. But just in case one of the contacts gets welded shut accidentally or stops working, this is a redundant method of breaking the current through the circuit. And the last one, which is very common that we will use, in fact, this is the one that we will use most commonly, is called a double pole, double throw switch. So double pole means it has 2 input connections, and double throw means it has 2 possible output connections per input. So you could attach a wire here to this connection, or you could attach a wire here to this connection. All right. Whereas here, there's no wire connection up here. All right. So there's only 1 input. There's only 1 input and there's only 1 output per input on a double pole single throw switch. But on double pole double throw switch, there are 2 possible output connections per input connection. So this is really common. ubiquitous almost, especially on relays. And we're going to use this in the next couple of labs. And if you go to a catalog, like one of those big, thick catalogs, they don't really print the paper ones anymore. They stopped doing that a few years ago because it used a lot of paper. But I've saved a couple of catalogs from years past from DigiKey and Allied Electronics and Mauser. Those are all kind of like parts warehouses for electric devices. And I still order stuff all the time from those catalogs. But if you go into their catalogs and you want to order a switch, well, there's going to be like 50 pages of switches. So you got to specify what kind of switch you want. So these are toggle switches, and you have to specify whether you want a single pole single throw toggle switch, or a single pole double throw toggle switch, or a double pole single throw, or a double pole double throw. These are all going to be different switches, obviously. So depending on your application, what you're building, you're going to want to specify a different kind of switch. So this is standard terminology in industry. Okay, the next thing we're going to talk about is relays. And relays are just a combination of a switch that we just talked about and what's called a solenoid. But before we get to talking about that, let's take a quick break. This is approximately halfway in this video, halfway through the material anyway. So let's take a quick break and stretch. Okay, let's go back and talk some more about relays. And in fact, the next thing I want to do actually is show a couple of videos. And these videos are going to talk about what a solenoid is, and I'll tell you right away. What a solenoid is basically just a coil of wire. A coil of wire, and when you send current through that coil of wire, it creates a magnetic field. And we'll talk a lot more about that in the second third of the semester. But for right now, you don't really need to know anything more about it other than when I send current through a wire that is wrapped in a coil, it creates a magnetic field inside and around that coil of wire. All right, so that's the extent of what you need to know about solenoids for right now. But this is a video that gives a little demonstration of that and how it can be applied to make useful devices. This first video is just a really short video about solenoid valves. We're not really going to deal so much with solenoid valves in this class, but it's a good introduction to solenoids. And solenoids can be used in a valve just like they can be used in a relay. In a relay, we're not going to have the solenoid cause the motion of a valve. Instead, the motion is going to be to change the position of a switch. So it's pretty similar, but it has just a little difference kind of at the end. So let's go ahead and watch this one.
A solenoid is an electric coil. When a battery is connected to the coil, a magnetic field is created and pulls a plunger or armature back. This opens a valve, allowing high-pressure air to flow into the pneumatic cylinder. When the battery is disconnected, the plunger is pushed back, closing the valve and blocking the flow of high-pressure air while letting air flow out of the cylinder.
The next video I want to show is just a little bit longer, a couple of minutes, and it talks about how to make one and a little bit more about the electrical applications of using a solenoid.
Electromechanical solenoids are devices used to activate anything requiring a quick and powerful linear motion. You probably have a number of solenoid-operated devices in your home. Power locks on a car are often activated by solenoids, and the numerous cycles of a dishwasher are controlled and activated by solenoids. Manufacturers use solenoids to control and operate the specialized equipment used on modern assembly lines. Solenoids function by using the magnetic field that appears when electricity flows through a coil of wire. The moving needle in this compass reveals the presence of a magnetic field. Well-designed coils can produce powerful magnetic fields. I'm going to build a simple solenoid using 12 meters of fine insulated magnet wire, a 4-inch common nail, a straw, and 4 AA batteries. I start by wrapping 12 meters of 28 gauge magnet wire close to one end of a straw, creating a coil. I have to leave both ends of this coil exposed. Magnet wire is coated with a clear insulator. I'm using sandpaper to remove this insulation, exposing the bare copper wire. This 4-inch iron nail fits perfectly into the coil end of the straw. Connecting the two leads to a battery, we witness the magnetic field moving the iron nail. Here I've mounted the straw vertically, with the nail extending from the bottom. I'm using 4 AA batteries to energize the coil. Making the final connection, the coil is energized and the magnetic field lifts the nail. Break the circuit and the nail drops. I'm using gravity to return the iron nail to its original position. Many solenoids use springs to return the iron core to its start position. I'm only energizing the coil for a few seconds. It can get hot. We can see how the linear motion of this mechanism could be used to control the locks on a door or open and close the valves in a washing machine. In robotics, if a quick motion is required, solenoids are often used. This is another device that uses an electromagnetic coil. It is similar to a solenoid, but it is used to control electricity. It's called a relay, an electromagnetic switch. You can see the fine wire coil in this relay. When the coil is energized, the resulting magnetic field pulls these two contacts together. They are joined to these two connectors. This is where you would connect a circuit. The contacts would switch it off and on. When I connect 6 volts to the coil on this relay, you can see the contacts closing. The specs for this relay state that it can control up to 10 amps at 250 volts AC.
All right, I think I'll stop it there. So the point that I want you to get out of that is, first of all, to see how it's made and just see a demonstration of how it works. But second of all, I want you to start getting the idea that a relay is made up of 2 parts. I'll say this again when we get back into the slides, but a relay is just a solenoid. Solenoid is a coil of wire, and when current goes through it, it creates a magnetic field. And if you have a metal plunger, we often call it a plunger, like that nail, inside of the coil, then it will cause motion. All right, so the solenoid with a plunger inside of it will cause motion. It moves. It causes something to move when you run current through that coil. All right, so that's the first part of it, of a relay. The second part is that motion, what it's going to do for us in a relay is move a switch. Right, so now this is, one way to move a switch is just by using your hand. You come into a room and you flip a switch. But another way to move a switch is by using a relay, where the solenoid is going to cause the movement of that plunger, and that plunger's movement will change the position of a switch. All right, so a relay is nothing more than a solenoid connected to a switch. All right, and we just talked about different kinds of switches, and we can use those different kinds of switches in a relay. Now we're going to talk a little bit more about relays and how we can use them, such as for the next lab. First of all, this is what a relay could look like. There are lots of different kinds of relays. This is called an ice cube relay. It's called ice cube because the components are contained in this clear plastic container, kind of like an ice cube. And this is what we have a bunch of these in the lab. So if we were in person right now, you would be using these types of relays to do a bunch of the practical applications that we're going to do in the next labs. Tinkercad also has relays, so we're going to use Tinkercad, and we're going to build circuits with relays in Tinkercad. So in Tinkercad, they don't look quite like this. It's a little bit different, but we'll go through that in the next video. So here's the operation of a relay. Like I said before, it's just a solenoid connected to a switch. So it's an electromechanical device, which means that it has electrical components. That's the coil of wire, and I guess you can consider the switch to have electrical components. And the mechanical components, well, that's the plunger that's physically, mechanically moving back and forth due to the magnetic field created inside the solenoid, and that physical movement moves the position of the switch. All right, so it's both electrical and mechanical. We say that's electromechanical. So the way it works is when you send current through the coil, the solenoid coil, it creates the magnetic field, and that is going to cause a force on the metal piston or plunger, and that causes the piston or plunger to move up or down relative to the coil. And then that plunger is connected to the switch, and so the position of that switch will change when the piston moves one way or the other. And so combined, we call that whole thing a relay. And these are the videos that I just showed you. All right, so we can build this up. We're going to build up a relay. We've got a switch. What kind of switch is this? Well, how many inputs do we have? We have two, 1, 2. So it's a double pole. And then how many outputs do we have per input? We have 2 possible outputs per input. So it's double throw. So putting them together, it's a double pole, double throw switch. This represents the plunger right here, and it represents that these are tied together. So whenever this switch moves, this switch has to move with it. So these two things have to move together like that. Okay, and then there is our solenoid with the plunger or piston inside of it. And so that piston or plunger is going to move up or down due to the force acting on it by the magnetic field, which is created by current flowing through that solenoid, through that coil of wire. All right, so that whole thing together is a relay. So let me stop right here and ask you, how many connections or terminals or pins are there on a relay? A standard, and this is a pretty standard, double pole, double throw relay. Well, all you really have to do is count them up. So how many places are there for wires to connect? So you already know that there are 2 possible inputs or commons. You already know that there are 2 normally open, and this is shown as a normally open, and this is a normally open. There are 2 normally closed connections right here and right here. And now there are going to be 2 more connections to energize the coil or the solenoid. So here is a connection, so it comes in and it goes around the coil and then it goes out there, or vice versa. So there were 6 connections for the switch, and then there are now 2 more to energize the coil. So there are a total of 8 connections that you will see on a standard double pole, double throw relay. And you'll see that in the next lab. All right, and then we have to have a way to energize that coil, and so we could have some other circuit that is going to energize the coil. And you might be thinking of yourself right now, well, this is kind of stupid. Like, we need to have a voltage source over here, so why don't we just directly connect this to whatever output we need over here? That's a great question. Maybe you're asking that right now. So there are some good answers to that, and I'm going to save that for just a little bit because there are some very good reasons why you would want to do this arrangement with the relay instead of just directly connecting the output of this voltage source or the output of this switch right here to this output over here. So why wouldn't you just want to directly connect it to the load, whatever it is? We'll talk more about that in just a little bit, all right? But first, let's label them. This is a common contact, so is this. This is a normally open contact associated with this common. This is the normally open contact associated with this common. This is the normally closed contact associated with this common. This is the normally closed contact associated with this common connection. So each of these would be like screw terminals, like where you could attach a wire. So this is important. I mentioned this already before, but when we talk about the normal position, normally open, normally closed, that means the position of the switch when the relay is de-energized, like you just pulled it off the shelf or got it shipped to you in the mail. So it's not installed in anything, it's not energized, it's nothing. It's just what's connected when it's de-energized. So we call a normally open contact, that's here and here, they are disconnected from their common contact when the coil up here is not energized. Conversely, a normally closed contact, that's here and here, they are connected to the common contacts here and here when the coil is not energized. That's why we call them normally open and normally closed contacts, respectively. Then when we close this switch right here, then we energize this coil that creates a magnetic field that exerts a force on the plunger, which pulls it, and that repositions the switch. So now we have a connection between the common and the normally open. So when the coil is energized, then a normally open contact is connected to the common contact when the coil is energized, and a normally closed contact is disconnected from the common contact when the coil is energized. All right, so here is why we would want to use relays in the first place. This is what I was talking about just a minute ago when I said, what's the point of all this? Why don't we just directly connect the output of this switch to the load? So there are some very good reasons for that. Probably arguably the most important reason is because you could have a lot more current and a higher voltage at these connections. So a lot higher current going through this switch or a lot higher voltage at this switch than you could have going through this circuit right here. And a good example, I think, is maybe a Raspberry Pi or an Arduino or a computer. But let's say we want to control a big motor, like the motor that's controlling air conditioning or HVAC ventilation system. All right. So do you think that you could power a big motor like a 4 horsepower motor or something like that, even smaller, even a 1 horsepower motor? Can you power a 1 horsepower motor directly from the output of a Raspberry Pi or an Arduino or a computer? No, you can't. You can plug in a USB, and at home I have a little fan that does plug into a USB. It's kind of cool, but it's a teeny little fan. I mean, it's probably like a 20-watt fan or something like that, a teeny little fan. So there is no way that you're going to be able to power a motor, like a sizable motor, with the output from an Arduino or a Raspberry Pi or any type of computer. All right, a motor is going to take way higher voltage and, importantly, way more current than a little computer can provide. However, you could have an Arduino or a Raspberry Pi or something. You could have it operate this little switch right here, and you could even have the Arduino or the relay, the Arduino or the Raspberry Pi. You could even have it power this coil right here, because that coil doesn't take very much current or a high voltage to energize. And then once you have this coil energized, now you can have some external power source, maybe a wall outlet. So that's providing your electrical power that will go through here and then power your load. All right, so although you can't power a large load directly with a control device like an Arduino or a computer or something, you can still control the output device by using a relay. So your control device, Arduino, Raspberry Pi, or whatever, it only has to provide a small control current to activate this coil. And then by doing that, you can control the large loads that are passing through the switch part of the relay. All right, so this is arguably the most important purpose. You can switch a large load with a small amount of current. Okay. Another good reason is that you can invert the signal. And what I mean by that is you can turn something off with an on signal. And you can do that by using a normally closed connection on the relay. In other words, if this turns on, then I could turn some output down here off. All right, and there's usually not a great way to do that except with a relay. Another good reason, number 3, is you can control multiple circuits with one switch. So if you have this type of switch, double pull, double throw, you could control 2 circuits. You got 2 commons, so you can control 2 circuits, but you can get relays that are 3-pole or 4-pole or even more. They get a little more expensive, but you can control a lot of different circuits with ultimately just one switch. Just this one right here can control all of these circuits down here in the switch part of the relay. And the last good reason for using a relay, your relay part, this could be in a remote location, let's say like a switchgear room, whereas this part over here of the control circuit, this could be like in an operator station, all right? Because if you are switching large voltages and large currents down here, it gets a little more dangerous. It's a little more dangerous to be switching 4,000 volts or 100 amps of current going through here. That's more dangerous, and there's a greater chance for arc flash to happen, like we talked about in electrical safety. So ideally, when you're making this switch, you don't really want to be standing right next to it if you can help it. Much safer to be in a different room. So you can control this part of the circuit in an operator station, different room, and you could have the actual switching of the loads, which is this part. You could have this in a different room. You'd have the whole relay in a different room, and that's just it's a safer way to control large, high-power devices. All right, some schematics here and some nomenclature that you're going to have to use. First of all, like I said before, I'd recommend you refer to the last 2 pages in your lab manual. In fact, I will show you. It looks like this. And this contains a drawing of all of the schematics that we are going to use in this class. It gives both the US, or I'd say North American, version of the schematic symbol and the international symbol. And for the purpose of this class, we are going to use primarily the North American ones. So when you are drawing your circuits, then I want you to use the North American. That is the column under US/Canadian. I want you to use the schematics under that column as you're doing the labs and drawing your circuits. All right, so for the present purpose, the most important ones for right now are to represent the coil of the relay. And sometimes we call them control relays, so they're abbreviated CR. And sometimes, lots of times, we'll have more than one relay in a circuit, so we'll number them. So we'll have CR1, CR2, CR3, etc. And we will abbreviate that CR1, CR2, CR3, etc. So this is how we represent the coil part of the relay. And then we also have to represent the contacts. So we have normally open contacts and we have normally closed contacts. So this is what a normally open contact looks like. Your wire comes in here and then it comes out here. So your common connection would be right here. I'll show you an example in just a minute. But your common connection would be right here, and then your normally open pin or terminal would be right here. All right, so you can see there's normally no connection between these two, so it's a normally open contact. and we label this CR1A. So this is a normally open contact from control relay 1. So CR1 tells us this contact is associated with control relay 1, or relay 1, and the A tells us that it is a normally open contact. All right. So the opposite of that is a normally closed contact, where you have just a slash through there. That's how you know it is a normally closed contact, and we label it CR1B. CR1 tells us that it is associated with control relay 1. Control relay 1 is controlling this. And then the B tells us that it is a normally closed contact. So your common connection would be right here. You'd have a wire coming in like this, and this would be your common. And then your screw terminal or pin for the normally closed connection would be right here on this side and go out like that. Another device that we're going to use in this lab is a pilot light, and the abbreviation or schematic symbol for a pilot light looks like this, where these are kind of like the little light rays that are kind of photons that are coming out of the pilot light. So label it PL1 for pilot light 1, PL2, PL3, so on and so forth. All right, so think for a minute. Here's one example of a schematic, and we call this a ladder electrical diagram. And I'm pretty sure that most of you have seen ladder diagrams before in the context of PLC code. This is not PLC, so don't get that confused. I often see students getting PLC code confused with ladder electrical diagrams, but this is not PLC. This is actually just a circuit. All right, so the way this circuit works is we have a voltage supply over here applied to this rail, and then our ground is over here. So you might look at this and say, where's the complete circuit? How is this a complete circuit? Well, it's a complete circuit because it's not shown, but there's a voltage supply, say up here, and the positive side of the voltage supply is connected to this side, and the negative side of the voltage supply is connected to this side. All right, so the complete circuit goes from the positive side of the voltage source to the positive side of the ladder electrical diagram, and then through the rungs as the logic allows, as the devices allow, and then back to ground, and then back to the negative side of the voltage source. Okay? All right, so what does this do? What does this ladder electrical schematic do? Think about that for just a minute. In fact, you might want to pause this video for just 30 seconds and think in your head, what's going to happen when I press that normally open start push button? What's going to happen? Okay, so what's going to happen when you press this normally open start push button, the push button labeled start, is you're going to have continuity through that push button once you press it. And then once you press it, then you will energize the coil of CR1, that's relay 1, control relay 1. Once the coil is energized, then any normally open contacts associated with relay 1 will close, and simultaneously, any normally closed contacts associated with CR1 will open. All right, so remember, these are shown in their normal de-energized state. So normally, when this thing is not pressed, when I'm not pressing start, normally I have 24 volts here, and I do not have continuity through this rung. Current cannot pass through this rung because there's a normally open contact here. So PL1 is de-energized. And normally when I have not pressed start, I do have continuity through the normally closed connection, CR1B. And so I do have current that flows through here and energizes PL2. So maybe we should talk about what happens before I press start first. So before I press anything, I just connect the voltage source and energize this circuit, but don't press anything. What's going to happen is PL1 is not going to be energized because we don't have current going through this rung, this component right here. but I do have continuity through this component, therefore I energize PL2. Okay, now when I press start, all right, so I'm going back a little bit. When I press start, CR1 energizes, so now all normally open connections close, normally closed connections open. So now I will have continuity through here, so current flows through here, and then I have a voltage applied here to PL1, so I have current flowing through PL1. So PL1 turns on. Simultaneously, this normally closed connection will open, so I won't have continuity through here anymore, and PL2 will de-energize. All right, here's another example. This is a very common example that I think you've seen before, probably, in PLC circuits, but even if you haven't, that's fine. So think for a minute about what's going to happen in this circuit. First of all, think about what's going to happen if you connect the voltage source, but don't press anything. Don't press any push buttons or anything. And then think about what's going to happen if you start pressing various push buttons. Okay, so first of all, what's going to happen if I just connect this circuit like this, but don't press anything? All right, well, I have 24 volts applied here. I do have continuity through the stop push button because it's normally closed. But I don't have continuity through here, so no current's going to flow through here because it's normally open. And no current is going to flow through here. I don't have continuity through here because this is a normally open contact. So I don't have continuity through either of these branches, so I'm not going to energize the coil of CR1 yet. Similarly, down here, I have 24 volts here and here and here, but this is a normally open contact, so I do not have continuity through it yet, and I will not energize PL1. So the answer, when I apply 24 volts here, I energize the circuit, but don't press anything, nothing happens. Nothing. Okay? But now what happens when I start pressing push buttons? Well, what happens when I press the stop push button? Well, then I break continuity from here to here, and so now still nothing happens. Nothing changes. But what happens if I don't press stop, but I press start? That's where something interesting will happen. When I press start, as soon as I press start, I get continuity through here, from here to here. So current is going to flow from here to here, and then it's going to energize the coil, that's this, of CR1. And so now all normally open contacts associated with CR1 will close, and all normally closed contacts associated with CR1 will open. Well, here we have a normally open contact associated with CR1. Same thing down here. So CR1A, that means it's a normally open contact associated with CR1. And this 1 right here means it is the first normally open contact associated with CR1. This 2 means it's the second normally open contact associated with CR1. All right, so when this energizes, CR1A1 will close, and simultaneously CR1A2 will close. All right, so in this top rung up here, once this closes, then I have continuity through here, which will continue to allow current to flow to the coil of CR1. So now, even if I release the start push button, it doesn't matter because I can have continuity going through this part and continuing to energize CR1. It's kind of weird to think about because it's like it's feeding itself, you know? It's like it's going through the switch part of the relay and then going through the coil part of the relay. But it works. It's perfectly valid to do that. All right, so as long as that's closed, it's feeding and energizing the coil of CR1. And this is now closed. So we have continuity through here. So we energize PL1. So PL1 turns on. You can probably already see how we can de-energize this. That is by pressing stop. So if I press stop, then I don't allow current to flow through this branch anymore. And so I de-energize CR1. And now all the normally open contacts return to an open state, and all normally closed contacts return to a closed state. So both of these will reopen. And now, even after I release the stop push button, I have broken the continuity, and so I will not have current flow through here, and I will not energize that until I press start again. And similarly, when this opened, I no longer have current flowing through here, and PL1 is de-energized. So what happens is you press start and release it. PL1 is going to turn on and stay on until you press stop and release it, and then PL1 turns off and stays off. And you might remember what this is called. It's called a latching circuit. It latches. It latches on to the coil. The coil latches on. Okay, here's an example. This is one of the last things we'll do in this video. Here's an example. Let's draw a ladder electrical diagram that does this. So I want you to draw a diagram kind of like what we just showed in the past two slides, but I want you to draw your own that accomplishes both of these functions simultaneously. This is one circuit, one ladder electrical diagram that does both of these things. When normally open push button A is pressed, so you're going to have a push button labeled A. When it's pressed, PL1 should energize. Similarly, you're going to have a push button labeled B. When it's pressed, when it's not pressed, PL2 is energized. All right, so take a few seconds and try to draw a circuit, a ladder electrical diagram that accomplishes both of these things. Here is our problem statement. When normally open push button A is pressed, PL1 is energized. That's a pilot light. When normally open push button B is not pressed, PL2 is energized. All right, so we need to draw a ladder electrical diagram to do this. So let's start by drawing our left side rail. And when we do this, we're going to use 24 volt sources. So there is our side rail. Don't forget to label that with 24 volts. And you know what? Let's just go ahead and draw the other one at the same time. So here is our right side rail, and don't forget to label that ground. Now, what we've got is two logic input devices. That's going to be push button A and push button B. And I'm going to want to control them independently because they're going to do different things. So they have different outputs. So what I'm going to do is have two rungs, one with normally open push button A and another one with normally open push button B. Okay, and I'm going to want to perform different things when each one of them is pressed. So the easiest way that I can see to do this is to give each one its own relay. So I'm going to do this. When A is pressed, it's going to energize the coil of CR1. And once I do that, then down here I can use whatever sequence of normally open and normally closed contacts that I want that are associated with CR1. All right, so this gives me lots of flexibility to do whatever logic operations down here I want. Same thing with push button B. I'm going to call this CR2. So now, whenever A is pressed, we're going to energize the coil of CR1. Whenever B is pressed, we're going to energize the coil of CR2. Now I can fill in whatever logic output I want down here. So the first part is, when normally open push button A is pressed, PL1 will energize. Okay, so here's PL1. There's my little photon waves coming out of that. Now, how do I make it so that when A is pressed, PL1 is going to light up? Well, when A is pressed, it's going to energize the coil of CR1, and that's going to open any normally closed contacts or close any normally open contacts. So in this case, I want to use a normally open contact so that it will close when CR1 is energized because A is pressed. So I need to label that CR1A. CR1 because it's associated with CR1, control relay 1. A because it's a normally open contact. And if I wanted to here, I could put a number 1 to indicate it is the first normally open contact associated with CR1. So I've taken care of the first part of the problem. The second part is when normally open push button B is not pressed, PL2 is energized. All right, here's PL2. And what logic inputs here do I want to control PL2? Well, I want PL2 to be energized when push button B is not pressed. When B is not pressed, the coil of CR2 is not energized, and so I want continuity through it, so I need this to be a normally closed contact. So this needs to be CR2, so it's associated with that relay, and it needs to be a normally closed contact, that's labeled B. And if I want to, I could put a number here. I could say it's the first normally closed contact associated with CR2. All right, so there's my answer. That's one answer. There are actually different ways to do this. In fact, you don't necessarily need relays here if I had not stipulated that these were normally open push buttons. If I had allowed you to use a normally closed push button, then you could have done something like this. So that meets the requirements for A, so I didn't really need a relay there. And then for B, I could have actually used a normally closed push button. So this has continuity through it until I press B, and then this is going to be PL2. So sometimes a common question that I get is, how do I know when I need to use a relay? Well, we talked about the 4 relay functions before. So if you need to do any of those things that we talked about, like if you need to invert the output, turn something off with an on signal or vice versa, then you probably need to use a relay. If you want to control a large load with a small current, like the current through here is going to be much smaller potentially than the current through this branch. So if you want to do that, then you need a relay. But in short, my answer is go ahead and try to do it without a relay, and that's fine. If you can do it without a relay, and if I don't tell you that you have to use a relay, then that's fine. Go ahead and use it without a relay. But there will be some times where I either tell you that you have to use a relay or I make it so that you have to use a relay. Just a few more things to talk about on the slide presentation. So here's the physical relay that you would be working with, but we're going to deal with the representation on Tinkercad in the next lab. So a few recommendations that I have, whether you're working in the lab physically with relays or when you're working with the Tinkercad representation of circuits. The first one is really important, and it's different than PLC. So this is really important to take note of. When you're drawing any type of electrical diagram, whether it's a ladder electrical diagram or a different kind of circuit or a wiring diagram, which actually shows physically which connections are connected. That's what a wiring diagram is. It physically shows which pins, which terminals the components are connected to. When you're showing any kind of ladder electrical diagram or any electrical diagram of any kind, you can only show each component once. That means a push button or a relay or an LED or anything. You can only show it once. So you can't have two push button A's, one on one ladder electrical diagram rung and one on the next rung and one on the next rung. No, you can only have one push button A, and you can only show it once. And the reason for that is because of electrical safety. Because if you're doing a lockout tagout procedure on something and you're looking at how to de-energize it, then you're going to look for how to trace back and find what to tag out to de-energize it. So if you've got the same component shown in multiple places on the circuit, how do you know how many places where it is? Is it shown once or twice or three times? And if you're trying to de-energize something and make sure it's de-energized, that's a nightmare. That's an impossibility to make sure that you're de-energizing something. So the way to deal with that is that we always only show a component once on an electrical diagram of any kind. Specifically when you're working with relays, use the description of the circuit. That's the qualitative description to draw the ladder electrical diagram. And then you're going to take the ladder electrical diagram to make the wiring diagram. And the wiring diagram is where the individual wires are connected. A big recommendation I have is don't try to use your intuition, because that can get you into trouble. Use the ladder electrical diagram to guide you as you're making these circuits, say in Tinkercad. The next one applies more to in-person manipulation of the relay, but it applies in Tinkercad as well. Make sure you don't install the relay backwards. Make sure that you're careful with which is the positive side and which is the negative side, because it matters. It won't work if it's installed the opposite direction, if the polarity is backwards. And the last recommendation is more of a general term. Recommendation is that slow is fast. If you work your way carefully and slowly through the labs and through the calculation problems, then you're more likely to get it right on the first try, which means that you are less likely to have to go back and redo it. So the quickest way to do most of these labs is to carefully and slowly think through them step by step, and don't try to skip steps and just jump to the final step. So think carefully through the problem. That's usually the fastest way to solve these problems. Okay, that's going to wrap things up for this video, where we've talked about different kinds of switches and relays, how relays operate and why you would use relays, and an introduction to ladder electrical diagrams. In the next video, we are going to talk about the next lab and how to do the next lab in Tinkercad. So I will see you there.